I guess one thing that I remember from this morning's talk is obviously this has been kind of billed as the tech inside for the market outside. And to be honest, I can't think of a better way of describing Hamamatsu and what they do, really. Hamamatsu as a company cover many, many different market sectors, from medical to high energy physics to, all sorts of industrial applications and things like that. So we cover 15, 16,000 products, something like that, across all these markets. And the vast majority of them you'll never see because they're inside other people's technology that they then use to basically get to their ends and their means to do that with. So last year, Hamamatsu celebrated the 70th anniversary of the company. So with that, I kind of wanted to take a step back and give some background as to how the development of our electron beam came by and how using different groups within our company, as well as collaboration with our customers, we've got to this sort of angle where we are now. So just in terms of our worldwide presence, then we ship to most of the world now, but our main office and manufacturing is all Japanese. And then we have major business groups in Asia around China, all across Europe, and then in North America, primarily in the United States. So if we take a step back those 70 years, we can start right at the beginning and look at how the developments and the market knowledge of our lamps and tubes groups combined with our X-ray group of all things have combined to get to where we are with the electron beam. So all the way back in the 1950s, the initial technologies that Hamamatsu kind of developed were what we call phototubes. And these are very simple glass-tubed products that are essentially give you an on-off signal. So you will have seen successes to this without knowing it. All the lights outside, especially now we're in winter and it goes dark earlier, when they switch on, it's technologies analogous to that, which essentially do all that work for you. And using that kind of lamp technology, we further developed that into light sources for analytical science and applications such as that. And that was kind of the first step towards using light for curing. So these kind of technologies were then optimized for spot curing sources for applications such as fiber optics and things like that. So manufacturing where they needed to cure resins and that kind of thing. Now, in the late 90s, it says 1970 there, it's not updated, but in the late 90s, then another one of our groups came out with what we call a microfocus X-ray source. Now, this might seem a bit left field in terms of where it comes from, but this is very important into understanding how an electron beam source works. So an X-ray or an electron beam source works the same at the start. So you have a very high voltage supply, and you use that to create electrons from a filament. Now, in an X-ray source like this, the filament is very tiny because you're directing these electrons in a very small beam. And you also aim it at a target, so a metal or something like that, and it creates X-rays through a process called Bremsstrahlung. But then if we want to make an electron beam source where, particularly in printing, you want to cover a wide area to cure across a web, then you can't get away with just having one tiny spot. You have to then extrapolate that out much wider. So in Japan, we developed in the late 2000s the original electron beam source we had, or EB engine as we call it. And this was used for medical applications for disinfection and things like that of old test tubes and organic matter. And this uses multiple filaments, and it's only about 50 millimeters across. So, of course, for an application such as printing, 50 millimeters is nothing, and you can't put them next to each other and extrapolate that out. So how can we take that technology and make it useful? Well, the lamp group that I mentioned earlier then moved on to LED technology as that became more and more commonplace in the market. So we start off with LED spot sources to replace the lamps spot sources we already had. And then as we moved on into the 2000s, then we developed more and more area curing ones and worked with our customers to develop very specific additions to those that could help them in their particular niches. So then we come to where we are today in 2024, so 70 years after that original glass product, with our new EB engine for inkjet applications. And so this is the initial version is a 450 millimeter wide one, so it's for narrow web applications, and there'll be a new 650 millimeter wide one at some point in the future as well. So there's a few things to note here, because anyone who may be familiar with electron beams already may know these as very, very powerful systems. So typically you're looking at, we're measuring kilovolts, but usually 100 to 200, maybe even more kilovolts coming out of this, which is very big, very bulky, requires a lot of power. So what have we done to try and reduce that outlay and optimize it for the inkjet market? So the first thing is, the smaller it is, the easier it is to get onto a printing press, particularly where you have applications where perhaps you're looking to retrofit or something like that. So by reducing the amount of power going into it, we can reduce the size of the machine and fit it in into presses that already exist. There are power supplies and things like that that are extraneous to that, but as with if you had a water-cooled system or something like that, it allows you to move that part of the system elsewhere. Now you might quite rightly say, Kane, but you've reduced the power there, so surely the performance is impacted and maybe it doesn't work as well. Well, actually, if you use a lower acceleration voltage, as we call it, so in this case, if you use 80 kilovolts like we do, so in that 50, 100 range, rather than say 150, actually from the tests we've done with inks and with collaborators, we actually find that there's a significant improvement by using these lower powers. There's an added bonus to this as well. So not only does it absorb more in terms of the ink, but because you're using less power, you're putting less energy into the substrate, which opens up more options for the substrate. So you can use, papers, metals, woods, all sorts of different things. And the other thing for EB inks is you can use photoinitiators and use it in tandem with UV if you really want to, but you also have the option to not use them at all, which gives you the option of avoiding, some regulatory issues on that. So to get these electrons firing out of this very big window, then you have a lot of energy going into what is essentially a metal film. And this heats it up quite significantly, so we have to make sure that that is cooled, and that is cooled uniformly, because if it's not cooled uniformly, you get different energy electrons out of your system, which means you get an uneven cure. So a combination of water and nitrogen gas is used around the output window, and then this is used to keep this uniform for long-term operation. So the idea is that you can stick it on and you can leave it printing as long as possible. Typically, these kind of systems use multi-filaments, so like the older version of the EB engine that we had uses multiple filaments to create these electrons. But this can lead to a wide variety of different energies coming out, which means you get different doses absorbed. So one thing we've done is reduce that multi-filament into one single large filament, which is no easy feat for that kind of width of detector. And then this is, as you can see, quite narrowly controlled within 10% of for uniformity. And then finally, and perhaps most importantly, when you're thinking about end users and what their overall goals are, then one issue with big shielded electron beam systems is the maintenance. Often it requires very specialist knowledge, and it requires, you're getting somebody in specifically to do that kind of maintenance. So to make it as easy as possible, the two main perishable items in a system such as this, which are the filament and the window itself, these are designed to basically come off as one very easily. So these can be changed in around about sort of 5 to 10 minutes once the vacuums of the system are, set down to atmospheric pressures. And so this allows us to train the customer themselves on how to maintain it, and it means that their downtime when they're printing with these kind of things is as little as possible. So this was just kind of an overview of where we are with this kind of technology at the moment. But as others have said today, Hamamatsu is very big on collaborating. So I mentioned we have about 15,000 products. Somewhere in the region of 60 to 70% of that is customized to our customers' needs. And that comes from direct conversations with people such as yourselves at conferences like this, but also at, regular meetings with our current clients as well. So please, I'm here for the next 2 days. So if you have any questions or, there's things that perhaps you've seen at the stand or on here that maybe don't quite fit what you want to do, please do come and talk to me, because we can accommodate different niches and optimize what you're doing. Thank you.